Okay, guys, come on, let us start the new chapter today. That is the chemical kinetics. Okay, this chapter is again quite easy chapter because most of the questions asked from this chapters are in form of the numericals. So focus more on the numericals. That is the order of reaction. We have zero order, first order reactions. Okay, T half are the reactions which we have to learn in this chapter. Now, a small brief of this chapter. Chemical kinetics. Now, what does kinetic means? Kinetic means speed with respect to time. Any particular chemical reaction gets over after some time. Now, we should know that time because in chemistry, in chemical, in the factory, suppose if I have an order to prepare 1 ton of ammonia, then I should know that looking at my size of the factory and the containers which I'm having, I must know that by what time my 1 ton of ammonia will get complete. Okay, so this chapter actually helps us to understand the timing part. Some chemical reactions are slow, some chemical reactions are fast. Okay, uh, a slow reaction can be made faster by adding or by changing some some external parameters like temperature, pressure. Okay, we can use the catalyst. Some reactions are very fast. Sometimes the reactions are so fast that we have to actually limit them. We have to slower them down by adding some inhibitors so that the danger aspect associated with the reaction and to its surrounding can be reduced. Okay. So what are these and how these actually work? This we are going to study in this chapter. Basically, this will give us the speed. Chemical kinetics is a speed. By what speed the chemical reaction is happening. Okay. So let us start with this. So first of all, chemical kinetics. So what is it? It is a branch of the chemistry. Branch of chemistry deals with the rate of reaction. It deals with the rate of chemical reaction. Rate of chemical reaction. Rate means something divided by time. Rate you can call it as a speed. Okay, something divided by time. Okay, so here we have a concentration. Concentration per unit time will give us a speed. We call it the rate of reaction. Now, any chemical reaction, if we see hypothetically, it is written as A, one reactant A reacts with another reactant B and gives us, say, a product. Let us say two products, B and C. Now, in this chemical reaction, what is happening? So, any chemical reaction can be written in this form. Okay. So, here, with the time, if I have to draw the graph, the concentration of my A and B. Suppose this is my reactant. I will start with some concentration of the reactant. Let me call it as a R. So at time is equal to 0, this is time 0, I will be having some concentration, initial concentration. With time, it will go slowly and gradually down. At the initial time, the product's concentration will be 0. And with the progress of the time, the concentration of the product will increase. So here we are getting two graphs on the same system. This is for product and this is for reactant. The concentration of the reactant is going down. You can say there is a change in the concentration of the reactant with change in time. The negative sign indicates that the concentration is decreasing. Now, the speed by which, suppose if I have 2 points, point A, okay, and there is a point B. If any vehicle is running or moving from point A to point B with the speed, with the velocity, because we are having drawn here a straight line. Let's say it is moving with the velocity of 5 meter per second. Okay, from A to B it is moving. So I can say a vehicle is moving from A to B with the velocity of 5 meter per second, or else I can say that the vehicle is reaching to B with the velocity of 5 meter per second. 5 meter per second. So what is the difference here? The difference is from point A, the object is going away from A. And if I see with respect to B, the object is coming towards B. This is what we indicate with this minus sign here. So the speed is same. An object is moving away with 5 meter per second speed from point A, but other way around, I can say the object is approaching towards B with the speed of 5 meter per second. Okay. So if I consider this as a straight line or the velocity, then I have to give plus or minus sign, because object is going away. Okay, I can indicate it by negative sign. If the object is coming towards B, I can say the object is having a positive speed. Now, why we are discussing this? Because in the chemical reaction, the speed by which my reactants are getting consumed, with the same speed, the concentration of product will increase. Okay, so concentration of reactants with respect to time, decrease in the concentration is equal to the change in the product with respect to time. So anything with respect to time is nothing but the rate. We call it a rate. This word rate is also indicated by small r. In many books, it is also given as a rate of reaction. Rate of reaction. In short, many times teachers may use the word ROR or capital ROR. So all these things are the same. Okay. Rate or speed. Speed is not very oftenly used word because this goes with some physics. So we are calling here it as rate, R or rate of reaction or ROR of the reaction. Fine. So if I have to give the ROR of this reaction, what will be that? So rate of the reaction ROR is equal to minus concentration of change in the concentration of A with respect to some time t, which is also equal to the speed by which B is disappearing. I can use the term the rate by which the concentration of B is disappearing. So both the rates will be same. Minus sign is indicating here their concentration is going down. What does it mean going down means? Let us say if concentration, initial concentration was say 100, and now after some time t, that is delta t, change in time. Okay, the concentration is now say 60. So what is the change in the concentration? Change in the concentration is always final concentration minus initial concentration. Initial concentration. The final is 60 minus 100. So I will get minus 40. Okay, minus 40. Now the rate, which is a scalar quantity, and cannot come in the negatives. The speed cannot come in negative. Velocity negative means it is going, it indicates a direction. So here minus sign, if we indicate as a direction, then it is okay. But when we are talking about the rate, this negative sign does not goes with the rate because it's a scalar. So what we do is in the same formula, we are putting minus initial. See the minus sign here. So that will give me a rate. Okay. So either you can say the rate, whatever the answer comes in the calculation, okay, so that will always be a positive, or else I have to write in a statement way. Okay, that the concentration of A is decreasing by so and so rate. Fine. So here now, this is clear that the concentration of A, the rate by which this A is disappearing, is equal to the rate by which B is disappearing. At the same time, you will find the rate of C increases by the same rate. The rate increases by the same rate. So this is d delta T upon delta T. So to calculate the ROR out of this 4, why I'm taking 4? Because here we have taken the equation, hypothetical equation, A plus B gives me C plus D. Okay, so either reactant or product, any one out of any reactant, if I know the concentration of any one of this, suppose I know the concentration of B only, so I am not dependent on the concentration of C and D and or A. By knowing any of the concentration out of this 4 here, I can calculate the rate of reaction. In fact, by knowing the concentration of one and knowing the rate of reaction, I can calculate the concentration of the other 3 unknown using this formula. Okay. Now, the reaction which we have assumed here hypothetically, that is A plus B gives me C plus D. This is my hypothetical reaction. Now, usually the chemical reaction does not occur in this way. We do have some stoichiometric constants number here, like A or B or small c or a D. Say, for example, if I have a reaction like N2 plus H2 gives me ammonia NH3. Suppose this is a reaction. Now, we cannot proceed with this reaction because this reaction is not a balanced reaction. So, as per the law of conservation of mass, I have to balance it. So, let me put here 2 and here I will put 3. So, in this reaction, what we have seen is there are some stoichiometry numbers. So, 3, 2, here there is a 1. So, what about what this stoichiometric numbers does? Okay, how does they affect the rate of reaction? So, these are the A. Now, the rate of reaction now will become ROR, rate of reaction ROR is equal to minus 1 upon the stoichiometry delta change in the concentration of A per change in time is equal to minus 1 upon B change in concentration of B upon change in time is equal to 1 upon C change in the concentration of C, the T, and similarly I can write 1 by D delta change D on delta T. So this is my another equation, not another but the same equation where we are having now stoichiometric numbers, where we have the stoichiometric numbers. There may be a stoichiometric number or there might not be. Suppose in the same particular reaction, suppose there is a no stoichiometric constant. Say the B doesn't have any stoichiometric constant. In that case, what we do is we don't write this here. This will not come. This will not come. Okay. So this is how we find the ROR, rate of reaction for any reaction. So rate of reaction, rate of chemical reaction is ROR. So the rate of decrease in the concentration of any one of the reactant or rate of increase in the concentration of any of the product will give us the rate of reaction with respect to time. Now this is the graph. Okay. Now what about this graph? Let us understand this graph. Rate of reaction, when we have studied the previous slide here, what we are assuming here, the reaction, we are saying let us find the concentration, okay, at point this. So there is a time t1 and there is another time T2. So what is delta T here? Delta T is time 2, that is final time T2 minus time T1. So we are actually finding the ROR for this journey, this highlighted journey. This highlighted journey. Okay, this path. We are actually finding the rate of reaction. What if somebody is interested in finding that I don't want the rate of reaction between two time intervals. I just want the rate of reaction at this particular time interval only, this point. At this point only, what will be rate of reaction? Exactly at the 5th second, exactly at the 15th second, or exactly after 1 hour, exactly. Okay, we are not interested between what is the rate of reaction between first 5 minutes or first 15 minutes. So in first 15 minutes, we have to see 15 minus 0. So I have to get an average of first 15 minutes. So in second point, what is asked here, that suppose if there is a graph indicating the formation of any product. Now I want the rate of reaction at this point P, exact. In that case, what we have to do? So in that case, we can only get it through the graph. And in that graph, what we have to do is, I will draw a tangent to this graph. There will be a tangent. And the tangent passing through the point, we can find the slope of this. So the slope of graph at a given point will give me ROR. How it will find? So simple formula is there, the x2 minus x1 upon y2 minus y1. This is the slope of the graph at this point. So the detail values will be given. This is your x2 and y2 point, coordinates of this point. Any point that you decide, any point on this line will give the same graph, same slope, x1 and y1. Right? So this is called an instantaneous rate of reaction. We call it instantaneous rate of reaction. And this you can find only from the graph. Okay. So first the data has to be given. From the data you have to draw the graph, and from the graph you have to find that time at which it is asked, the specific time. And at that point you have to draw the tangent and you have to find the slope, and the slope will give you the rate of reaction. Now, so far we know that now the rate of reaction is dependent on the concentration. Okay. Now, which are the other factors? Let us say, which are the factors which affects the rate of reaction? Is the rate of reaction is affected by something? So let us make the points. Okay. Factors on which your rate of reaction, that is ROR, is dependent. So the first, let us say, here is nature of reactant. Nature of reactant. Suppose I have a hydrogen which explodes very fast. There is an explosion if I burn it. Explosion. And I have a wood. The wood doesn't explode, but it burns slowly. So you can see that the speed depends on the nature of the substance which we are using. Number 2 point. We have concentration of the reactant. Concentration of the reaction. Reactants. Okay, reactants. Already we have known the formula ROR is equal to minus 1 upon A concentration of your A upon delta T. Sorry, minus 1 upon A change in the concentration of reactant divided by change in time. So concentration, if is more, definitely the rate of reaction will be more. Third point, temperature. Temperature. Simple exercise you can say, suppose if you have a potato, you have to cook the food. You simply can't keep the potato in the water and just wait that it will get cooked. No, you have to give the temperature. Some reaction, in many chemical reaction, we have to give the temperature so that the rate of reaction becomes faster. Okay, so temperature. Then we have fourth point as temperature, then catalyst. Now, catalyst is very important. What it does actually. Okay, catalyst is a chemical which lowers down, which lowers down the activation energy EA. We call it EA, activation energy. Activation energy, okay, by providing an alternative route or path to proceed with the chemical reaction. Okay. For example, what is activation energy? Now, suppose if I have a matchstick and I have to burn it, without rubbing it on the matchbox, it cannot burn, or without giving it a light lit to it, it will not burn. That means initially I have to give some energy. So the energy of my reactant, okay, is, let us say, it's at this level. So I have to increase some energy. I will increase some energy. And once the sufficient energy is obtained by my reactant are, okay, sufficient energy, we call it the activation energy. So it is a minimum energy which is required by the reactants to get converted into product. So once it gets that activation energy, it starts converting into product. So there is a possibility that the product may end here. Let me say product 1, case 1. Okay, case 1. Now in this case, if you see the difference in the energy level, this is EP, it's the energy of the product, this is energy of reactant. The product EP is greater than energy of the reactant. That means the product have absorbed energy. What type of reaction we call it? We call it endothermic reaction. These are endothermic reactions. Now, what is the another second case? There is a second case that the reactants, the products may go down and become stable here. Now, let's in in product 2, we will find that the EP2, let me call this is EP2, this is EP1. Okay, EP2 is smaller than E reactant. That means energy of reactants is higher than product. So here energy is released. Energy, the excess energy which the reactant were having, it is released in the surrounding by the product. Product has a less energy. Energy is released. So this type of reactions are called exothermic reaction. Okay. So this is one graph question which has been asked in the board. In one of the board paper, I saw this graph. So by looking at the graph, you have to tell that how the reaction is endothermic or exothermic. Now let us move to the next topic of the chapter. That is the next point. Next point after catalyst is fifth point. Can say is surface area. Surface area of reactant. Now, more the surface area, faster will be the reaction. Okay, so that is why mostly during the chemical reaction, we prefer that your reactants are in the smallest possible particle size. That is either in the crushed powdered state or they are dissolved in some solvent, so that the more particles are available for reaction at a time. Okay, so that you can understand. Like suppose if I have a big particle, so only the particles reactants which are at the surface are available for the reaction. What about these particles which are in the bulk? They will not participate in the chemical reaction. So they have to wait till this outer particles get reacted and get converted into products. So if I break this particle into small particles, then most of them are now available for the chemical. Okay. So surface area, smaller the surface area, faster will be the rate of reaction. Now let us have next. Now we have a next topic is the rate law. Rate law. Now this is an important part of this chapter. Okay, this is an important part of this chapter. Many a time in the chemical reaction, it is not possible for us to find the concentration of the reactant or the product every time. Okay, because we are not going to go into the boiler of the reaction and find out. Sometimes the reactants or the products are so harmful or maybe delicate or very reactive, whatever the reason is, but we cannot calculate the concentration of the reactant. Okay, so in that case, how will you find the rate of reaction? So in that case, rate law actually helps us. Okay, so what is the rate law? The rate law is it is mathematical relation. Rate is equal to, okay, the rate is equal to concentration of my reactants, product of the concentration of the reactant to some stoichiometric number, some stoichiometric number. Okay, it is proportional to, instead of equal to sign, can say it is a proportional. Now, what is M and N? We will discuss later. So the rate is equal to, or you can say ROR is equal to, this is another way of finding rate of reaction, is equal to K. K is a rate constant here. Concentration of A raised to some power B, concentration of B raised to the power N. Okay. Now, what are M and N? These are known as a order of reaction. M is known as a order of reaction. Order of reaction with respect to A. What is N? N is order of reaction with respect to B. Okay. And if we add them, m plus n will give me order of reaction. Okay, what is m? Is the order of reaction with respect to A. What is n? It is the order of reaction with respect to B. But if we add them m plus n, then we get the overall order, or you can simply call it order of reaction. You can call it order of reaction. Okay, so in exam, this question is asked in 1 mark. Say, for example, for some reaction, A plus B gives you C. The rate is given as rate is equal to K. Okay. Instead of K, there might be some number written. Say, for example, you can write some number here, 5 to 10 to the power 2. The concentration of A, say 3 power 2 to 2 power 1. Okay, so this is the concentration of your A. This is the concentration of your B, and this K value is written here. Find it as well. And they will ask what is the order of reaction. What is that? The order of reaction is nothing but the sum of the powers 2. Here you will find 1. So order of reaction for this reaction is 2 plus 1 is equal to 3. Now order of reaction may be in fraction. This powers may come in the fraction. Say like you may get a rate for any particular reaction. A is equal to A 1 by 2, B 3 by 2. So what will be the order of reaction? The order of reaction will be m plus n, assuming m this is equal to m equal to n. So we have to add 1 by 2 plus 3 by 2 is 4 by 2 is equal to 2. So order of reaction is 2 for the reaction. Okay, so this was about the order of reaction. Now let us find some units of rate of reaction. Another unit of rate of reaction. In our syllabus, we have zero order, okay, zero order and first order. These two order reactions are there, okay, and later on we will find the pseudo order, pseudo first order, pseudo first order reaction. Okay, so we have to focus on 0 and 1 only. Second order reactions are not there in our syllabus. So let us say that let's find the value of K, units of K for zero order. So order of reaction rate is equal to R. Rate is equal to K. Let us have another reactant as A. Okay, because we are talking about now zero order. We are calculating zero order. The unit of K, unit of rate, unit of rate constant. Rate constant. Rate constant. So it is 0. Anything raised to power 0 is equal to 1. Anything raised to power 0 is equal to 1. So now here rate is equal to K. Now what is the rate? Rate, we know that it is a change in the concentration, change in the concentration with respect to time. The change in concentration will give you concentration only. The unit of concentration is moles per liter divided by, and unit of time will be second, is equal to the unit of K. So what is the zero order K units for this? It is equal to moles per liter per second is equal to unit of your K for zero order. Similarly, you can find the unit of K for first order. Let us say for first order reaction. First order reaction, again, the rate is equal to K reactant raised to power 1. Raised to power 1. So unit of K. The rate is again concentration per unit time. So that is mole per time, or moles per liter, and the concentration of A, that is moles per liter per second, is equal to K. What is the unit of this concentration? Again, it is a moles per liter. So moles per liter here and moles per liter here will get cancelled out, and you will get the value of the unit of K as second inverse. Similarly, you can find the order of reaction for any order reaction, for any order of reaction. And you can get a general formula. You can derive a general formula. Okay. So if I minimize this, and instead of going with individual, you can directly write the unit of K is equal to concentration, that is moles per liter 1 minus n second inverse. Okay, suppose if I have to find the unit of K for a third order reaction. So we are not going to calculate through this long method. You can remember this formula and directly apply. K is equal to moles per liter 1 minus 3 second. This will give me moles liter square second. Okay, so this is how we get the unit of K for third order reaction. Fine. Let us talk about the zero order reaction in some details. Zero order reaction. Which are the zero order reactions? Zero order reaction, or we can say that integrated rate law for zero order reaction. Integrated rate law for the zero order reaction. Now, we are not going right now in the exactly derivation of this. Okay, so let us first write the direct relation. Okay, for K, how to find, because order of reactions, again, when we have rate is equal to K concentration of A raised to some power m into concentration of B raised to some power n. When we call that some power m, some power n, how do we get these values of n or n? Now, these are not theoretical values. These are not the theoretical values. These are practical values. What does it mean? We have to do the various set of reactions, various experiments. Okay, and from that reaction and the data obtained, we have to find the value of m and n. These two are these powers, these numbers are not the theoretical values. So we cannot get it from any chemical reaction. Okay, by simply writing chemical reaction, we cannot find the value of m and n if they are obtained from the experimental values. These are the practical values or the experimental values, which are done after doing several practicals, drawing graphs. Okay, so again, m and n are not possible to find every time, so we have to integrate now them. Okay, so in that we get another integrated rate of law. integrated rate law, and that helps us actually now to calculate the order of the reaction or the time taken for particular reaction for its completion. So for zero order reaction, K, that is the rate constant, is equal to concentration of the reactant, initial concentration of the reactant minus concentration of the reactant at given time t divided by time. This is your equation. Okay. We also can find the half time, t half. What's the meaning of the t half? T half is actually the time when your initial concentration of the reactant gets converted into half of its value. Half of its value. Say for example, if I start with 5 kg of my reactant. So what is T half? T half is that time when my 5 kg of the reactant reduces to 5 by 2, that is 2.5 kg reactant. So half of my reactant is consumed. Okay, that time is called the T half. So how do we get the T half for the zero order reaction? So you can directly put the values here. Okay, here. So you can make the formula T is equal to R0 minus R at some time T divided by K. Now in this reaction, in this equation, then I have to put T half R naught minus what is this RT? Now RT has become the R naught by 2, half of my original concentration divided by K. So this value will give me value as T half is equal to concentration of R naught on 2K. Now see the very important good thing in this equation, this reaction, sorry, this equation relation. Okay, T half does not have to do anything with the concentration of my reactant at time t. At time t. Okay, I don't want this R that after 5 minutes, what will be the concentration? I am least bothered about that. Why? Because the formula doesn't require here. We just need the initial concentration. So when we start any chemical reaction, we always know the initial concentration. So if you look at this T half is directly proportional, to initial concentration of my reactant. 2 and K are the constant values, so I can merge them in equal to sign by putting a proportionality. Okay, so if I get a graph, okay, if I get a graph, concentration of reactant versus time, I will get the straight line. Okay, so more the value of R naught, more will be the value of T half. So there is a direct relation, and for direct relation, we get the straight line. Okay. Now let us understand the first order reaction. How the first order reaction proceeds. First order reaction. First order reaction, again, we are not deriving it right now. Okay, K, the value of K for the first order reaction is given by 2.303 upon T log of initial concentration upon concentration R at some time T. Okay, from this you can also get what is T. So by rearranging, T is equal to 2.303 upon K log of initial concentration upon concentration of the reactant at some time T. Okay, so from this we can calculate T half. The T half is equal to 2.303 upon K log R naught over R naught by 2. Okay, so if you calculate this, put this value R upon R naught, this value will get cancelled. So log 2, 2.303 log of 2 upon K is the T half value. Okay, so log 2 into 2.303 will give you 0.693. Give me, this is a constant value, log T is again a constant value, 0.693 upon K. Half. This is again a nice relation where T half is independent of the concentration, initial concentration, as well as the concentration of the reactant at time T. So it is not dependent. T half is not dependent on this. Okay. So this is how we calculate the values. Or you can directly say that by this and these two values, if I merge it from this T half is proportional to 2.303 is a constant, rate constant again is a constant, proportional to the log of R naught upon R. So if I get the graph log of R naught upon R and T straight line, then this graph is of first order reaction. First order reaction. Okay, so remember, fine. So guys, we have completed a big important part of this chapter. Pseudo first order reaction, just small glance of pseudo first order reaction. Sometimes what happens that A plus B gives us C plus D. Okay. By looking at the chemical reaction, we assume that the reaction appears second order. Okay, second order. But what happens is the concentration of one of the reactant is so high that delta change in concentration of B, one of this reactant, is almost negligible. Is almost negligible. That means concentration of B. It seems that change in concentration of B is not there. It's a so big value. Okay, but when we write the chemical reaction, though we have to write B, we are writing. So sometimes a false interpretation is done by the observer looking at the chemical reaction. So by looking this reaction, it seems it is second order, but because the concentration of B is so high that the change in concentration of B actually does not exist for the reaction. In that case, B is not an active participant here. So we talk about only A. So this type of reaction, this is the first order reaction. The reaction is first order reaction. First order reaction. But falsely, it looks like a second order. So we call it pseudo first order reaction. The pseudo first order reaction is a reaction which appears what? Second order, but actually it is first order. And why it happened? Because one of the reactant is in very high concentration, and the change in that concentration is almost negligible compared to the change in the concentration of my other reactant. Okay, so such reactions are known as a pseudo first order reaction. The example given in the book is for esterification, hydrolysis of the ester. Fine. So guys, today can stop the class here, and very few topics are now left in this chapter. Okay, that can be done as a part of a revision. Main crux of the chapter we have done here. Index questions are very, very important. Almost similar type of the questions are asked in the board. Again, board does not make experimental paper with this chapter as well. So here you can see the hydrolysis of the ester is given. Okay, so almost theory, kinetic molecular theory, kinetic theory of the particle you have studied in physics as well. Same uh, physics concepts are coming here. So they are given much detail in your physics syllabus. So you can learn from there. So after learning that, this small portion will become easy for you to understand. Okay. So for today, let us wind up the class today. So here we completed another big important chapter. The chapter is basically numerical based chapter. Fine. Okay. Fine. Thank you.